Hello everyone. In today's lecture, we'll have another example how we can implement the backstepping control, and also we have the MATLAB simulation for the same. So let me define the problem. Let's consider we have the nonlinear system. Nonlinear system x1 dot equal to ax1 square plus x1 cube plus x2. And we have the x2 dynamics, x2 dot equal to u. So this is quite highly nonlinear system. And here design control U to stabilize x1 and x2. We'll start solving the problem. We'll find the controls for the system. And finally, we'll have the MATLAB code for the same solution. So the process of backstepping design, it's remain to be same what you have done in the earlier examples. So let us consider x2 as a virtual control, which is denoted as x2 equal to lambda, for example. So lambda is here is a virtual control. In the previous example, we have alpha 1. So here we are assuming lambda. And for this, we have the system, the first subsystem, which is basically x1 dot dynamics, yields to be x1 dot equal to ax1 square plus x1 cube plus lambda. And let's consider the Lyapunov function. So I'm just going through some step jumps that the same process I'm not following what you have done in the previous examples. So I'm using some straightforward method. So consider a Lyapunov function as v1 x1 equal to half x2 square, and taking time derivative, okay, let us define this equation number 1. And taking time derivative, we have v1 dot equal to x1 dot, and here x1 into x1 square plus x1 cube plus lambda. And let us define this equation number 2. So now in this equation, we have to choose lambda in such a way that v1 dot is negative definite. So we need to choose lambda in such a way that v1 dot less than equal to 0. So for that, we choose lambda equal to minus k1 x1 minus a x1 square minus x1 cube. Now where k1 is greater than 0. So this is the virtual control first subsystem. And let us define this equation as 3. Now substituting this expression in equation 2, we'll have the, not 2, we have to substitute this expression in equation number 1. So substituting equation 3 in equation 1. So if you substitute in place of lambda, this lambda, so we have, or here also we have, I think we have missed one more part here. So now this lambda, equation 3, substituting equation 2, we get v1 dot is less than equal to, sorry, we can write equal to minus k x1 square. So this we can say negative definite, right? And now if you substitute this equation 3 in equation 1, so we have the x1 dynamics, we can write x1 dot equal to minus x1 square plus x1 cube plus lambda, or we can write a x1 square plus x1 cube minus k1 x1 minus a x1 square and x1 cube. So here this one get cancelled, this one also get cancelled, and we left with a minus k1 x1, and this is globally asymptotically stable since k1 is greater than 0 here. The steps we are following now, you can follow the same steps for designing control for the nonlinear system. In case if you are designing the control for aircraft or any other dynamical system, you can follow the same steps to design the control. So now we'll introduce the second error between x2 and lambda, the process we followed in the previous example. Now we introduce error between x2 and lambda and analyze this error to achieve stability. So here we introduce the error E equal to x2 minus lambda, and we have x2 as it is. In place of lambda, we can substitute the expression we have obtained by equation 3. So we can write plus k1 x1 plus a x1 square plus x1 cube. And from this we can write x2 equal to e minus k1 x1 minus a x1 square minus x1 cube. So this is the, let us define this, the equation number 4. Now we'll define x1 dynamics in terms of error. This error, what we have defined here. The same steps we have followed in the last example, in the last lecture. So further, x1 dot in terms of error, we can write x1 dot equal to, already you have x1 square plus x1 cube plus x2, or we can write, so in place of x2 we can write this expression, equation 4 here. So we can write, so we are writing the x1 dynamics in terms of error and x1 variables. So here we are writing ax1 square plus x1 cube minus plus e. So in terms of x2, we are writing this expression. So here e minus k1 x1 minus a x1 square minus x1 cube, from which you can write e minus k1 x1. So if you notice this x1 dot dynamics, this is written in terms of error and x1 variable. So we can write denote this equation number 5. Now we have to also find the second error dynamics. So now we have to find the error dynamics E dot in terms of U. What you have done in the earlier lecture. So we can write E equal to x2 minus lambda and E dot equal to, so we have already found the x1 equation here, and we're now writing the E dot dynamics and what you will be considered for finding the overall stability of the system through the Lyapunov. So E dot you can write x2 dot minus lambda dot, and x2 it is given in the problem E equal to lambda dot, and also we know that lambda equal to minus k1 x1 minus a x1 square x1 cube. This already you have obtained lambda before this expression, right? And from which we can write equal to lambda dot, we can write minus k1 x1 dot minus a, or 2a x1 dot minus 3x2 square, x1 square and x1 dot. From this we can write minus k1 plus 2a x1 plus 3 x1 square x1 dot. Or we can write further, in place of x1 dot, we can write e minus k1 x1. This already have found. Sorry, it is here, equation 5. So in equation 5, you can use here. So we can write minus k1 2a x1 3x1 square into e minus k1 x1. So from which we can write, we can substitute this lambda dot here. So let us define, this is equation number 6 and this is 7. Substituting equation 7 in 6, we get E dot equal to U plus K1 plus 2AX1 plus 3x1 square and E minus K1 x1. Right. So here we have the two dynamics, E dot dynamics and x1 dot dynamics. So you can use equation 6 and equation 8 for the stability analysis using Lyapunov. So let us consider the Lyapunov function as V2 x1e equal to half x1 square plus half sorry, e square. And from this, we can take the time derivative v2 dot x1e equal to x1 dot plus e dot. So we can substitute x1 dot dynamics and e dot dynamics here. So we can write x1 equal to e minus k1 x1. Already we have the x1 dot dynamics plus e. We can write the expression of e dot here, which is k1 plus 2a x1 plus 3x1 square into e minus k1 x1 and plus u. We can write, yeah, we can write this. And from this, we can write k1 x1 square plus, we can take this term x1e inside this bracket. So we can write e into, we can write x1, this is the term x1 u1, sorry. So we have taken this term here. So e x1 plus k1 plus 2a x1 plus 3x1 square e minus k1 x1 plus u. Now we have to choose u in this equation in such a way that, so let us define 9, such a way that the v2 dot is negative definite. So for this we can choose u in equation 9, which makes v2 dot less than equal to 0. So to achieve this condition, so we have to modify this u accordingly. So you can choose as u equal to minus x1 minus k1 plus 2x1 plus 3x1 square into e minus k1 x1 minus k2 e. Now, if we substitute this term here, so this is 10. Substituting equation 10 in equation 9, we have v2 dot x1e. We can write k1 x1 square plus e. We can write x1 plus k1 plus 2a x1 plus 3x1 square e minus k1 x1, and we can substitute in place of u this whole expression. So we can write minus x1 minus k1 plus 2a x1 plus 3x1 square and e minus k1 x1 and minus k2 e. So here this term cancel out, and this term cancel out. So we can write from this k1 x1 square minus k2 e square. Yeah, we have found our So this is basically, you can say, negative definite. And for this condition, we can write hence x1 t et goes to 0 as t tends to infinity for all initial conditions x1 0 and e0, right? So also we can write here, now if you put as in this condition, the condition for what I have found, x of t and e of t goes to 0 as t tends to infinity. T tends to infinity, right? So as for this condition, x2 also going to 0, because the equation we have written equation 4, which is function of x1t and e of t. So if x1 and t and e of t's are going to 0, x2 also going to 0. So we can write here also from equation 4 as x1 of t, e of t goes to 0, and x2 t also goes to 0 as t tends to infinity. So we have found our contours for these particular examples. Now we'll go to the MATLAB code. This is the code. Yeah, this is the MATLAB code. And so whatever the function we have considered in this example, it is here. So this is the initial condition, and this is the initial values. This is the time period for simulation 10 second, OD 45 to solve the OD. And this is the function where we have taken a equal to 2, k1 equal to 2, and k2 also 2. In some example, why this value we have considered, we have also explained in first few lectures in this topic. And this is the lambda expression, and this is our control, and this is our dynamics, x1 dot and x2 dot. And these are the figure, to plot the figure. And this is the result. So we can see that as time tends to infinity. So here, this is basically x1, sorry, this is x1 of t, and this is x2 of t. So if you can see that as time tends to infinity, the response of these plots goes to 0. So system is stable. This is how we can design the control for the nonlinear system. In next few lectures, 2 lectures, we'll be considering this concept for the aircraft system, how we can design the control for the longitudinal dynamics and lateral dynamics of the aircraft. Thank you.